Happy to see you all. Thank you for taking the time. As you know, we have a lot of momentum with the South Carolina Fraunhofer USA Alliance. We now have approved more than 15 projects that we have ongoing with industry base here in South Carolina. We're excited to continue to offer different kinds of technology solutions and expertise in partnership with our university friends and other academic partners here in the state. We're kicking off today with technology on laser and some of the expertise and capabilities that exist within the Fraunhofer Center, in particular on laser applications. And I'll turn it over now to Dr. Marcel Schaefer, our South Carolina-based Fraunhofer colleague, for an introduction to today's presenter. Please feel free to put questions in the chat. We'll be allowing plenty of time after the presentation to let you ask questions, either verbally or we can relay them to the presenter on your behalf if you put them in the chat. And we're ready to get started. Marcel?
Thank you, Suzanne. Welcome, everyone, and welcome to 2022, where everything will be better. Welcome to the first webinar of our monthly webinar series. We ended last year with a huge topic, 5G. We want to start the new year with another huge topic, laser, specifically for automotive. Dr. Standfuss will present on laser-based applications, coatings, joining technologies for powertrains, interiors, components, as well as treatments for e-mobility. Interesting topic. We are very excited to hear about this research and real-world applications. So let me introduce Dr. Jens Standfuss with Fraunhofer IWS, standing for the Fraunhofer Institute for Material and Beam Technology in Dresden, Germany. Dr. Jens Standfuss has a Master in Material Science from the Bergakademie Freiburg and Technical University of Dresden. He received his PhD in Mechanical Engineering from the Technical University of Dresden in 1998. However, he already joined the Fraunhofer IWS in 1993, which, if I make the calculations correctly, means he will celebrate 30 years with the Fraunhofer IWS next year. I'm not pointing out how old you are, I'm just saying how much passion for the applied research with Fraunhofer and the broad experience you bring with us today you bring. Dr. Jens Standfuss led the group Laser Welding since January 25. He's head of the business unit joining. Since July of last year, Dr. Jens Standfuss is responsible for the business area development team at the Fraunhofer IWS in Dresden, and is one of his focuses on mobility. Today he brings us 4 different stories, each with a happy ending for the corresponding customer. Looking forward to hear those stories and the happy endings. So before I hand it over now to our speaker, Dr. Jens Standfuss, I'd like to remind everyone, hold your questions until the end of the presentations, put them into the chat. We'll get to them later, and please stay muted until we open the stage for questions. And now, Jens, the stage is yours.
Yeah, thank you, Marcel. Thank you, Suzanne. Hello, everybody. It's a pleasure for me, let's say, to start the year with some things about laser, especially in automotive. Maybe some. I hope you see my slides. What is the content? I will only give some information about Fraunhofer IWS. Marcel say something about who and where we are and what we are doing. And like Marcel said, I will tell you some stories, some developments for laser and automotive, starting with a topic which we are working since more than 20 years, welding and powertrain components, and let's say some examples how we do this and what is the benefit, let's say, at the end for the customer. Laser hardening is one thing, information system and possible applications for a wide range in the automotive things. And last but not least, 2 things which are relating together. One is high productivity laser clouding, especially for brake brake discs for especially for new cars in the electromobility, where some new requests are coming from the use, and connected with this, not only the coating technology, only how we can, let's say, get some information, non-destruct testing using lasers, so-called Welding technology for quality control of coatings and surfaces in general. And last but not least, feel free to get questions, and I hope I can answer you. And I see also here in the audience, my colleague Maria is here, and if there are some special questions, especially to Welding, I think she can assist me to help your question, to answer your questions. I think you are familiar with Fraunhofer coming from the previous webinars. Short things to Fraunhofer Institute for Material and Deep Technology. We are approximately 225 people for permanent staff. We have guest researchers, especially PhD students, also do. With a budget around 30 million and industrial revenue, especially last year. It was a very hard year, I think, for everybody in the which are working in the research, industrial research, so it drops a little down to 30%. Normally we are on the range of 40%. Industrial revenue means direct contract research with companies from Germany, but also from Europe or from the US. We are working in, let's say, with the laser technology in two main topics. One is laser materials processing, coming from cutting ablation, microtechnology, joining. I will come give some examples, thermal surface technology from hardening and coating technology. But as well, we use laser for some hot topics like additive manufacturing and printing, but also for the chemical surface technology and PVD, where I don't want to touch here in this. From the history, we comes with a very deep understanding from the material behavior. This is our background, and this are we connected with the processing technology from laser materials processing. I think we are well connected, and in Europe and also in the US. In Germany, there are two centers nearby here in Zwickau. At the university, there's a Center for Optical Metrology and Surface Technologies. And since many years, especially in the coating technology, we have a center in Dortmund together with the steel producer, ThyssenKrupp Steel, working on PVD and ceramic coating technology, especially for steels. In the eastern, we have a connection to Wrocław, to Poland, where we have a project center too. But the oldest one, I think, is in the US, and one is in Plymouth, the Center for Laser and Applications, CLA, and also I see Thomas, I think here is a member at the CCD in Lansing. I think since beginning in the 19th, there is a connection to these centers where we are very have a good connection and history with the people and with the technologies. What are the use cases, what I want to present you and to talk with you? One is a very old story, laser welding, especially for high fatigue loaded powertrain. That's one topic. The second one, using laser for hardening and mass productions. I will give you some information to process the systems on possible applications. See here many parts. And the second one part for the surface topic is laser cladding. An example for brake discs, like I told you in the beginning, brake discs, especially for the for electromobility, where some new requests are coming from. And last but not least, connected to this, if I code some things, I must have also a tool to characterize the coatings and the surface. And I will give you some information and showing what are developments and system for laser acoustic surface testing. That should be the storyline for the next, I think, 20 minutes, and hopefully I can give you some interesting information for our developments. First part, first topic, laser welding and component design for high fatigue loaded parts. Especially in the automotive drivetrain. What is the challenge now? I think the market situation for powertrain components in the last years is very hard connected to the drivetrain components. There is a rising number of this. We speak about transmissions with 7 to 8 or to 10 speeds. It's a very complex part. But we have also now electromobility and components for this and hybrid drives. And one thing is differentials axles. What is common and to all of this application is this is increasing performance, especially also with the development of high power motors and especially with the electromobility. Lightweighting is a thing that means decreasing dimension and weight is one thing, and one solution to solve this problem is, let's say, laser welding. But we have some challenges with this, and like I told you, coming with higher torque moments, we have an increasing weld seam load. And we need some high-strength materials, and from the welding side, it's more difficult to weld these materials. And in the next minutes, I will give you some information how we try to solve this problem and what is our procedure to do this and what we can offer you. I will make an example on this to show and explain you a little bit more in detail. For example, for differential welding. I think this part we need for all kinds of cars. If we speak about normal combustion engines or we speak about electromobility, and all of this will be a differential here. And normally it's in the past it's not welded. It's fixed by screws, and we need a very long thick flange. We need these holes and rings for the screws and the screws themselves, and we have 8 to 16 screws to fix the housing with the ground wheel. And since many years, laser welding comes more and more in this because it's faster and we can save weight. We don't need the flange, we don't need the screws, and this saves money and weight. And this is the driving force to speak about laser welding for differential gears. But there is a challenge from the material side. We have a ground wheel, case on it steel, and the cast iron housing. And from the weldability, we have some challenges with the high carbon content of both materials. And so we have extremely high hardening inside the seam, and we have a risk for cold cracks. So we must have some technology proven by with respect to the material and to the parts themselves. And the solution as well is from the beginning, from the welding side, well, if we have some hard to weld materials and some high strength materials, if the weld are ductile, we have a chance to weld it without cracks. And it needs, let's say, from in more detail, to minimize the so-called latable ridge formation in the heat affected zone of the cast iron, and so we get some perfect welds to this. But anyway, requests are sent. Welding machines are flexible, and you can use it for different type of parts. So anyways, the question from the customer is reduce welding time, reduce the weld seam wise with respect to this portion, reduce the material degradation to have a high performance part, and have a good process window. But all these requirements above are, let's say, a little bit counterproductive to the process window and the requirement, especially precision. What is the history? Oops. The history. We started this development more than 20 years ago using classical CO2 laser and pillar wire, and start here production for a German company in ZF. I think they are also in the US, and this first application where we are talking to and where we have these slides, this is a differential here from Mercedes-Benz for the M-Class working in producing in Tuscaloosa, and this was the first application of this. Starting here with CO2 laser and filler wire. Filler wire means a nickel-based filler wire, and it's very tricky to have a deep weld seam and to have a homogeneous distribution of the filler material. So there was some development to use a foil, which has the advantage you can increase the welding speed, and so the processing time drops down. But and this was the question from the customers, why we need this filler wire. And when we speak about nickel, we have a price of nickel around 80 to 120 euro per kilogram from this filler material, from this nickel material. This means per weld, per part, we speak about 30 to 40 euro cents only for filler material. And this is one thing which, if we have some 100 or 1,000 parts, then it's a high number of amount of cost for filler wire, and so we want to speed up these the welding speed to reduce the processing time. And that's why with new lasers we have this chance, and we can speed up by a factor of 3 the welding speeds with this. But the welding speed is one side. You have some requests to the product quality and how you can handle this. And our procedure is that we get a closed loop solution. Not only the process, we give also the design of some values to design the part and to design the weld, and you have both connected with the process. Means we can offer some special FAM solution to adjust the weld seam to the stress situation. But there are no, let's say, dimension values for this special material combination. So you need some test for to get some design values for the weld seam themselves. So it's a complex loading. You have some tension, you have some torsion, and we can do this by this way that we simplified test parts, but with the request that we have the stress situation according to the real part. We can test this by axial and torsional loading and get some stress strain curves to this for the dimensioning, and then we can optimize the components design also with the knowledge of the process themselves. And at the end of the day, what is the advantage? And, I hope you can see this video and you see both that's on nearly the same part with the same dimension. It's a process, the old one, let's say, starting around 2000, and now it's a state-of-the-art process. And we see this high speed during Formula 1, supported steel welding. At the same time, you can weld up to the double amount of parts with less distortion, with a higher torque moment to transfer from the load compatibility. And this is an advantage what we can offer to you. Offer to you means we have the complete process development, process chain together with some customers or producers from equipment. And at the end of the day, there is let's say, a collage from parts which are here going to our labs, to our development center here for this powertrain components. And I hope I can show you that we have don't only weld some let's say some coupons for test parts, so we can offer you the complete process chain beginning on some basic trials up to real components and transfer all this knowledge from one hand to the customer up to the process start in the production line. This is the first application. Laser beam hardening. What is the challenge generated for hardening? Conventional hardening technology using furnaces, induction or flame hardening, and that's our time and energy consuming. And the distortion is directly connected to the energy what you put in the part, and that's why laser hardening offer you a good thing, because you can minimize the heat input and you can integrate it quite easily in existing process line because it's quite fast and you have short process time, and you can offer we can also get an automatic quality control. What it means, only some slides to here. Hardening tabs for laser hardening is normally up to 1.5 millimeter, and I think with this hardening depth you cover a wide range of application for gears, for stamping parts, for tools, and so on. The advantage is compared, for instance, to induction hardening, you need no liquid or gas as quenching media. You use the self-quenching from the part sensor, of course, to minimize heat input only on the surface. And so you get the maximum hardness, showing here for tool steels up to the maximum hardness over 800 Vickers hardness. That's approximately 62, 63 Rockwell. And you have a very efficient process because the absorption on the part is quite high, and so it's a very good process. But what you need is some systems to control this and to integrate and be flexible, and also use the flexibility of such a process. And what you need is two. You need a beam forming to shape the laser beam, adapt to the part, and you must control the temperature, the heat input, depending on the geometry and the heat conduction of the part. And both can be offered. Both there are some developments, some real-time measurement sensors to control the process parameters, and all and this connected to a beam forming to adapt the beam. And showing here in the part, you see it's a quite wide range of change of geometry, and the process runs automatically. You have a wide, up to 60 millimeter wide track for hardening, and adapting the process parameter by scanning laser power and also the scanner parameters automatically to the surface composition. And this without programming. You program only the, let's say, based on some experience, on some values, the hardening depth to the material, and the geometry changes will be controlled automatically. And this is a very wide range of geometry. So it's a very flexible tool, at least this the beamforming unit and also the temperature control system with to harden complex shapes. And this is very flexible. Some examples here you show turbocharger shaft servers in running example, because there are different kinds of shafts in the diameter, and we substitute the classical induction hardening because for each geometry we need a coil, a tool, and the laser, it means the software connecting to the part, and you can save money. Rails, bearings, balls, there are different kinds of applications for laser hardening. Summarize, what is the benefit? You have a very efficient surface hardening technology. You can minimize the energy consumption. You can minimize with this the heat input, and so you have some parts with very high hardness and low distortion. So reworking is maybe in many cases not an issue. And the second one, it's very easily to integrate in existing machines or production. And so I think tools like laser beam shaping, temperature control are needed for this, and this can be offered, and it's quite proven for different applications, like shown here in this picture. Laser cladding of brake discs. Normally, at least brake discs are not coated, but with the new requests, especially for the electromobility, there are some new challenges for brake discs. With the energy recuperation, so the use of this brake disc is lower than normally, and so you have some corrosion, and that's why you need some cladding technology to do this. Laser is one possibility, but why laser? What is the benchmark for other processes? Thermal spraying is one side. You can have a coating thickness very thin. You can do this for a large surface. You have a very low heat input, but the coating structure is quite heterogeneous, and the adhesion of the coating to the substrate is quite low. Plasma arc spraying is one. This also do it trackwise. Different coating thickness is possible, but the heat input is quite high, and the dilution of the the base material is up to 80%. And if you compare this to laser cladding, you have a very high resolution. This can be good, but you can also use, like showing in the next slide, a very high efficiency through very wide tracks. And the advantage is the heat input is low, and especially the dilution of the base material, which leads to a change of the composition of the cladding layer, can prevent. And so you have a very high quality clad. To push the productivity, we are now able to use this with high power diode lasers. There is a very good development in the laser on the laser side, especially for high power diode lasers. So it's increasing power available for less money, and it is not normal, I think, that you get more for less money. And this is a very good thing to do this. How it works. Now you see this high clad process with a high dynamic beam with a high speed, using laser power up to 20 kilowatt laser power, and you get a very high productivity with this process. The coating thickness is around 0.2 to 0.5 millimeter, and you have a good combination of long-term corrosion protection of this part. And with this coatings, you can cover this this risk or improvements which is needed. And this is coming from the corrosion resistance, where you need a improvement for this, and the reduction of wear, and especially of the reduction of fine dust emissions with respect to the environmental requests, which are harder and harder for the automotive industry. And at the end of the day, a tailor-made solution without carbides or with, you can adapt the composition of the cladding layer to the requests from the part. Speak about costs and laser power. Now, with the availability of high power lasers up to 40 kilowatts, you can adapt by, let's say, selecting the laser, your efficiency. Efficiency means efficiency, and this means achievable productivity in, let's say, square meter per time per year. So there are some values to calculate this and to give you some input. What is the right process? What is the right laser power? And what can you expect with respect to the meshing costs, powder costs, and the energy costs? And so you can adapt your process to your requests in a wide range. If you have some coatings, there are some requests to characterize the quality of the coating and also the quality of the interface. And one method is the so-called laser acoustic surface testing. Some step backwards, what is the challenging in generally measuring or determining the mechanical properties of coated components with non-destructive, let's say, technologies are in a wide range unnecessary. That means for pistons, for cylinder liners, for electrical heaters like these are thermal spray coatings, like shown before, brake disc coating for laser cladding, but also for many other parts. And which are master control is the, let's say, the quality of the coat of the cladding layer, of the layer, with respect to pores, cracks, and also delaminations, characterize the thickness, the homogeneity, and this should be fast and effective with a high throughput. And one principle how it works is the development of the so-called wave, non-destructive quality control for coatings and surface. How it works and how what it has to do with the laser. Oops. Sorry. So first, you get an acoustic wave by a short laser pulse, which send, let's say, a mechanical wave through the part and transmitted to this, and it goes through the coating and through the substrate as well. You measure the propagation, the velocity, and also the frequency of this surface acoustic wave. And this is a piezoelectrical element and the necessary equipment to store the data. And then you see from the values, especially from the propagation values, from the phase velocity over the frequency, some so-called dispersion curves. And based on this dispersion curves, you get some different values with respect to the coating technology. And at the end of the day, you can measure and determine non-destructive, the Young's module, for instance, of the layer. So you get some information of the density, you get some information of the depth of the layer, and also of the hardening, for instance, and also if there are some damages inside, porosity, cracks, delaminations. And that's our offer you, let's say, you have a very wide range of information about the quality of the layer and of the interface for this. And this works non-destructive. Like shown here, for some laser arc coating for chains using a BMW. The coating is done for chains to reduce the wear and also to lower the friction resistance, the friction, and you get some effort about some 10%, something like this. And this is transferable to different things. And we can also use this for the showing to beginning. What you can, or you don't need at least some state-of-the-art destructive testing and characterizations to this. And at the end of the day, you get some very interesting things for this, and this in a very short time. At the end of the day, we can use such system. We can offer a complete adapted system also to the requests of the customers. So it means we have some properties, mechanical properties you can characterize without destructing, non-destructive. We are quite fast. It's adaptable to different applications, and you can get a customized system. And the advantages about, let's say, state-of-the-art systems like nano-indention is you have a faster measurement, you have no calibrations, you have less consumables, and you get more information with a higher precision. And I think both the process development, showing again for the laser cladding in combination with such a lathe system, you have a complete solution for cladding and also for the characterization of the process quality and the quality of the part themselves. This should be some short story about the possibility of lasers. And if you have some questions, please feel free to do this. And I will stop sharing, I think, my presentation, because then I see you and the chat room once more again. Thank you very much.
Thank you, Dr. Jens Standfuss. Thanks for the interesting topics you bring along. I understand we can't hear all the different companies that you work with on the slides for of course, IP reasons and stuff. But now the stage is open for questions that whoever in the audience might have. Now is the time, ask our expert. I mentioned at the beginning, almost 30 years in this field, so you can't get any better. Please. Some questions, otherwise I'll have some.
Early in the morning in the US, yeah?
It is early and cold morning.
It's
so
early and cold.
People need to warm up a bit.
I'll start with a question.
Yeah.
Jens, so I thought it was interesting on the BMW example you showed, where you can reduce the wear and tear right?
Yeah.
And the friction, presumably that's, something, a technology approach that's applicable for any kind of manufacturing equipment. Is that a good assumption?
Yes, but it's a special thing for, let's say, reduced friction of like this change and also for gears and
Okay.
coatings. I don't speak so much detail for the coating technology at this point. It's the so-called laser arc technology, where we also use a laser for these carbon coatings. And the advantage is, especially if you have no lubricants for the in the part. So that means it works like dry without any lubricant. So you can reduce the friction in a very high value.
Okay.
This is where, or this is the reason where some application in coating of gears, coating of chains, and also some piston rings are in the combustion engines. That's why it's very interesting technology.
Okay. Thank you.
On top of that, what would be typical customers? Like, can you explain some of the customers you're working with in Germany? I'm wondering if some of those customers also have a presence in South Carolina. Of course, that would be an easy.
I think that are nearly all suppliers which are, let's say, producing gears like ZF or other companies. I think they are also represented in the US, maybe also in South Carolina. And that's are, I think, for many applications worldwide, especially for the OEMs and the suppliers, using the same technology in Germany like in the US, if you think about automotive components. And so also see producers of equipment, laser machines, coating, producer coating technology. That's our the normal customers for our technologies. And that's also the suppliers support themselves for engines, like I said, or for transmission gears. That's the normal. BMW, Mercedes, ZF. Yeah.
The big ones.
The big ones, but also the small and medium enterprises specialized, for instance, for coating technologies or for laser welding machines.
And I assume that now that you're talking about the customers, this is not applied research, but also applied research that was already put in practice. So this is something that is on the market, in place, in the cars.
Yeah. So when you think about laser welding, for instance, so it's our aim, let's say, is that you get one solution or you have one face to the customer. So many colleagues are working from the beginning to this project up to the end, if it starts in the production line, so that you have this knowledge from one hand. This is one side. On the other side is what I told you at the beginning. There's a very long collaboration, for instance, with the colleague in the US at the Laser Application Center in Plymouth, Michigan, where we have an exchange of people between here in Dresden, Germany, and the US. And so there's a very good transfer of knowledge and technology from Germany to the US, because not all technology and especially testing equipment can be hold in the US. So there are many things developed here in Germany and then transfer to the center in Michigan. There's a very strong collaboration. And also in the other way, if there are some requests from the US coming via the Fraunhofer guys in Plymouth, for instance, for the laser side, and it's needed some special development, there is also a connection to us where we can work together at least.
Yeah, I mean, Fraunhofer USA is all connected, right? We have the Fraunhofer Center Midwest in Michigan, and the laser division, of course, is working with you for a long time. Thinking again about South Carolina, laser hardening was very interesting. So you mentioned lightweight, very flexible process, and then again thinking about the South Carolina manufacturers. Can you tell for this topic specifically again what the problem is that you solve with the technology? So what is the typical problem that those manufacturers have that you would solve?
there is, let's say, a wide range of application. Some example. In a stamping factory, you have some tools, and the wear, especially on some edges, and the tool is quite high, and that's why there's normally a very expensive process of hardening inside the oven. This is state-of-the-art process, let's say. And for this, there is already the need. There are only some parts or some regions of the part which needed to harden. And if this is the case, so laser hardening is and very interesting things. And then the customer comes to us. The other is induction hardening. Induction hardening is a very efficient process, also quite cheap. But if you have a wide variety of parts, the geometry, I showed this example for the turbocharger. There are some wheels with different shape, different geometry, and state of the art. Some induction hardening machines where if you have another batch, you must change the coil and the shape, the tool at least, and then it goes. And for such application, especially if it goes to, let's say, lower number of parts with the same size, but more flexibility or variety in parts, then laser hardening makes sense, and that's all typically the customers coming to us. So small and medium enterprises, companies which offer hardening technology in generally, but which are now faced to the, let's say, the challenge that they have a very wide range of, let's say, geometries, or at least only one part with one size, and where the costs for classical hardening technologies like induction or oven hardening are too expensive. And at this point, laser hardening makes sense, and is a very good solution. That's also typically customers ask.
Thanks, and that's very unique to Fraunhofer IWS, or is it like, what are the outstanding things you would point out for Fraunhofer IWS?
I think for Fraunhofer IWS, it's typically that we not only offer, let's say, the process development, and then you get it, and you must have a look where you get a system to transfer this. So we try to offer the whole things, let's say, and it's starting with some basic knowledge based on the experience and material and science from the process, but we have also some systems and solutions for systems. There are some unique solutions for laser hardening and beam forming and measurement systems, but also some very good collaboration, let's say, with some small and medium enterprises. Of course, we cannot offer all machines in this, but we can focus on the laser typical things, on the system, from the measurement systems, on the beam forming, and then together with some customers of handling and automation systems, we can integrate it in a line. At this point, we offer like a supplier, starting with the first, let's say, shoot on a testing part, feasibility tests, if it's possible, up to the end of the day of the production line. And, this is the typical way, especially for laser hardening, where we offer process development, but also system development for special adaptation of this, together with some suppliers.
That is working with Fraunhofer, yes. Thank you. We have a question in the chat. I'm reading out loud. Could you discuss further the material compatibility for welding of powertrain components? Are there any standard materials used, and are there dissimilar materials you may be working on welding?
Oh, please, can you repeat, or
Yeah. Could you discuss further the material compatibility for welding of powertrain components? Are there any standard materials used, and are there dissimilar materials you may be working on welding?
So for the powertrain components, so from the application side, there are some given materials at least. So there are requests on strength, on petted strength, but also on the wear resistance. So at least we are facing with the challenge that we cannot change, or that we cannot use the material if we want this. So in the most cases, there are some conditions around, and that's why there is a knowledge needed how to handle this existing material. That's a classical case hardening with steels with molybdenum alloy or manganese up to complex steels. And we need or we offer, let's say, based on our material science knowledge, an adaptive technology. So there is no, let's say, favorites on material for welding. From the customer side, it's normally not possible to change the material in the wide range, maybe in some cases, but normally we are facing with the challenge. They are hard to weld materials, but they are good for corrosion, good for friction resistance, good in strength, and this must be welded as it is. And this is the challenge for the welding development. It's maybe not the right answer what you want, but we don't prefer, let's say, to fabricate materials. It's good weldable, but on the other side, it's maybe too expensive, or the properties of the materials are not facing the requests, at least. That's why, for instance, for the differential gears, that's our cast iron, because that's a complex part and you must cast it, so it's given. You need, with the request to higher torque moments, you need high strength materials, and you can change this, so you must have a solution for this challenge. That is our approach to give this solution.
I hope that answers the question satisfactorily. Suzanne, do you have a question?
I don't.
Okay, so I saw it because you unmuted. So if there are no more questions in the chat, I would at least like to know where are we going with those technologies? Like you said, this is already in practice, but of course you continue to do research on these topics. So what can we expect in the next year or long term? What is the next big thing that you will present in 2 years?
I think in all cases is this now we have some systems to control processes, to control the quality, but I think we must step forward in the direction that we get some information not only on the quality of the process, but on the quality of the parts themselves. Means we must facing the whole process change with respect to control mechanism, and I think sensor systems to control the quality, to control the process automatically and adapt this is one thing. Using artificial intelligence is one topic at least, but not to do this because it's nice and a thing which all people doing. I think we have some first steps now running, for instance, for fatigue-loaded parts, starting in the aircraft industry, where we use high-speed cameras, where we use acoustic emission sensors, where we use also the light imaging and other sensors, and get a closed-loop control. And at the end of the day, let's say, get also some closed loop to predict the properties, at least, or change in properties. And I think this will be more and more coming using the new world of AI adapting to processes. And this is very interesting. And this has also some advantages, at least for the customer in our mind, because for many applications you have, or if it's some quite hard applications, there are sometimes some slightly changes in material in previous process steps, and then the process runs out. And, such technology, sensors, and these systems around, and this of artificial intelligence, and have respect to all things around the process chain, it offers the possibility, let's say, to get a remote control or remote assistance from far, and this you can adapt quite faster processes, and I don't need to travel to the US to solve maybe or some for troubleshooting, for instance. And this is especially for automotive industry and some automated processes a big issue. Sometimes if there stops a line because there's a very small problem, I think this is one one puzzle to solve this problem in the future.
Yeah, we see that,
yeah.
Right? AI is getting to the manufacturing floor more and more, and those who don't want to align with this will fall behind. This is certainly something that is dominating the next years in manufacturing.
Yeah. And from the laser side, maybe so electromobility was touching at the beginning. I think it comes more and more, and on the other side, there are also some new laser sources in the visible range. So it's also from the process side and from the system side some quite interesting developments. Because, like I said, I think one laser is one of the only or one thing where you get now more quality for less money, and from the laser systems themselves, and I think this is a little bit unique. Yeah.
Thank you.
Okay.
If there are no more questions, I'd like to remind everybody that even though all the technology that Jens provided us with is located at the IWS, Fraunhofer IWS in Dresden, of course we can do project together, and you would do a local project within our Fraunhofer USA South Carolina office within the Alliance, where the state would actually match half of the money for the project budget. So you do work with locals and get the technology, cutting edge technology from the Fraunhofer IWS. Last chance for any questions to our expert, Dr. Jens Standfuss. Thank you very much, Jens.
Thank you. Thank you, Jens.
Thank you.
Thank you too. I want to remind everybody we have another webinar coming up next month. Stay tuned on that. Several topics in discussion. We will inform you about that, of course. You will get the recording of today's webinar shortly in the next couple of days. You will also get the slide deck where you have all the dense information, and you can skim on that again and reach out to us. No problems. Of course, we are happy to connect. We're happy to answer questions that may come. And thank you everyone for joining, and up to a good start, I hope.
Thank you from my side as well, Jens, for being with us today. We really appreciated that interesting overview. Thank you, Marcel, for reminding us that folks that are on the webinar today can reach out to either you or I if they'd like more information, if they'd like to follow up on this topic. And our communications team will be sending out the information, as Marcel mentioned. We'd also like to ask you if you have some particular technical topics you would like to see. We'll be sending out a question to you about that. We've been picking things that we believe are of interest to the industrial base here in South Carolina, but if you have a burning desire to hear one or the other technical topic, please let us know, and we will try to find the right people within the Fraunhofer network to make those presentations for you. So we are here to respond to industry demand. Thank you everyone for joining us today. Happy New Year again, and have a good afternoon.
Yeah, thank you everybody.
Thank you.
Yeah, thank you. Thank you, Suzanne. Thank you, Marcel, for organizing. Thank you to all.
Thank you. Bye-bye.